infinite, and then you use both CZ and HZ process for this monocrystalline. But when you go for multicrystalline, obviously the grain size is going to reduce to less than micrometers. And this multicrystalline can also be formed by cast, sheet, and ribbon process. And this polycrystalline and multicrystalline, as their grain size is too small, normally the deposition techniques are applied. So in this, we are going to concentrate on single and poly, that is mono and poly, two major what you say major type of silicon that we are going to use, and which is again formed in bulk, not by deposition technique. Deposition technique is a second generation technique, so we will not look into that. So let us start with the lowest grade silicon, that is metallurgical. As I've said, it is obtained from the raw ore called as quartzite, and this is relatively pure form of sand. Of course, sand is SiO2 and some other impurities. So this is purer. Of course, that's what I said in the last lecture, that even though it is the eighth abundant, and we have got lots of sand on the beaches and sea. So you add this quartzite. Of course, you need heating, and if you remember the melting and boiling point, roughly.
You're not audible, I guess.
Hello.
You're not audible.
Yeah, that's what I said. That's what I said. My PC is showing poor network quality. So till what time you were able to hear?
So right now, just like 3 or 4 seconds. But yeah,
So
right now
this
you're audible.
production of MGS, right? Can you
Yeah.
see the slide?
Yes, sir.
Yes, sir.
Yeah, okay, so this is what, yeah, okay. So I was talking that sand is silicon dioxide, but you cannot purify it. The quartzite is relatively pure form, and that is what we use. We mix it with carbon, and then we melt it. Of course, it is electrical melting with carbon electrode. The point is, the melting point is roughly around 1500 Kelvin and boils at 3200 Kelvin. So above that melting point, we are going to melt it. And the crucible, I mean, the pot in which this is melt, it is made up of quartz, because that is the material which can sustain such a large temperature, such a high temperature. And at that time, we also see we are purifying. So definitely none of the what is a element, or none of the apparatus should be releasing its own impurity into the being purified material. So that's why quartz is used, so that quartz doesn't react with this quartzite or carbon, and it doesn't induces its own impurity. So thermal reaction of these quartzites will work up somewhere around 1600 degrees Celsius, and you can see SiO2, that is our quartzite, we combine with SiC, and ultimately you get the silicon in a liquid form. You remove all the sludge, and then whatever you get is about metallurgical grade. So of course, recipes are different, but roughly you get 98 to 99%. This is also a zone process. It means it is not in one go. There are several reactions which are taking place simultaneously in the whole furnace. So you can see here from the top, you are going to add the carbon materials. The released flue gases will be released at the top, and you will keep on getting this liquid silicon at the bottom. And of course, this process is in different zone depending upon the temperature. At the top somewhere around 1600, and at the bottom it will be around 1800 degrees Celsius. So these are the four-step reactions you get, and ultimately you will get silicon, which is roughly at around roughly 98% pure, which we call it as MGS. So this is 98% pure, but as we have to literally melt the whole of the semiconductor, so it's a very high energy consumption process. And if we talk about the numbers, it takes around 13 units per kg. So that's a huge electricity consumption, and that's why, I mean, that is one of the reason why this the production of silicon is confined to certain countries where the cost of electricity is very low, and at the same time you get good quality of electricity or good quality of power, that continuity and the fluctuations and everything. You know what is power quality. So uh, Norway, Canada, Brazil. And see, now you can also understand, I was talking about the vertical integration. So there are very few companies, especially nowadays, they are coming up, which will have plants literally from purifying of the silicon to making the wafer and to the making cell and the module. Just yesterday, there was a plant in Turkey that I think the company name is Velion or something. That is one of the company which has said that they will go for vertical integration of about 1 gigawatt of what you say total production in the year. So they will start literally from the quad side, and they will end up having the solar module. So that is the one
We are not.
factor, at least for a few years. Hello. My network is fantastic. Probably it might be your poor network. Okay. Whenever the network is bad on my side, I get some indication from MS Team. Okay. So next stage would be to purify this MGS further, and we call it as electronics grade. Remember, solar grade we will not be talking as of now, because it might lead confusion, and it might lead also the break of this whatever we are talking. So let us keep that silicon grade out of the question for as of now. As of now, we will come back to that. So let us talk about the electronic grade silicon, and this will carry in 3 steps before we make the wafer. So step 1 is production of trichlorosilane, that is SiHCl3. So this MGS, whatever we get, is converted into a low boiling temperature gas, and this is so that it can be purified to a level of particle per billion, that is ppb. So that itself will have 99.96. Okay, so this MGS is pulverized into fine powder, so that we increase the area, and it can then react with the HCl, that is the acid what we use. So we pass the HCl in form of gas, and that reacts with the fine powder, and it makes the trichlorosilane, and the hydrogen gas is released. So this reaction is carried at fluidized bed reactor. We'll talk about this FBR reactor in a while. In a simple sense, I'll tell you that it is a continuous process. Because this fine powder will keep on coming inside the reactor, and it will keep on reacting with the passing gas. So as I've said, it is a low temperature process. It is carried at around 300 degrees Celsius in presence of certain catalyst. Now this we have produced the gas trichlorosilane, and then next step 2 is a purification of that gas. There are 2 routes which we can follow for purification. So during this route 1 and this step 1 of the route 1, the impurities such as the iron or aluminium, they are going to react with the chlorine which is present in the gas, and they make the halides. Okay, so these halides, whatever FeCl3, AlCl3, obviously that is that we don't want. So it takes away these impurities. I think in 10th or 12th, especially if you are from CBSE, you have learned such a purification process. So you have to understand that we cannot purify or we cannot remove each and every kind of impurity in just one stage. We require a different philosophy and different ways to remove these impurities, and that's why it is always a multi-stage process. Okay. So next, the boiling point of this trichlorosilane is very low, and then fractional distillation. You have already studied for petroleum products. So see, in similar manner, this fractional distillation is carried. So again, at different temperatures, different what you call it as different products which are formed in this whole reaction will be taken out. So you can see that the major electrically active impurities, I think we talked about that, mostly the metal impurities like iron, copper, silver, gold, aluminum even. So these impurities are always are all removed at this particular stage. And that's why, in a quick, just one pass, we get much better semiconductor as compared to the MGS. Now I have got one question. Of course, you know what is doping, right? We'll revise it later. But you know doping, and I told you that in last lecture that phosphorus or boron are good impurities, right? Are good impurities. They are good atoms. Then you can see that I have mentioned here that we are also removing this phosphorus and boron. Can you tell me why, how? Not how, but why? If we want for phosphorus and boron, why we are removing right now?
To decrease its concentration.
But we want for phosphorus and boron, na?
Not in high concentration.
No. Certainly we will be having much greater concentration compared to 1 ppb when we dope it.
Sir, maybe it got moved when we are removing AI and CFC.
Not AI, it is AL. It is AL for aluminium. Okay. Huh. And what you said?
It got removed when we are removing aluminium, iron, copper automatically.
So no, but why we are concerned with the phosphorus and boron? They are good for us, right? As I've said, good bacteria, bad bacteria. So these are good things. Huh?
So maybe the at this stage the purity level of them, like we don't want it. So that's why.
That's what I
Sir, they
said.
may hamper
Certainly
the
we want it. Huh?
sir,
Yes.
they may hamper the doping concentration.
No. See, that's why this is not a technical question. This is a common sense question now, because see, you initially remove whatever impurities you want, are there, right? Try to purify it as much as possible, and then when you want to dope it, see, we require a very fine control of the material. That's why you cannot say that P and B are there, let it be there, then we will count it. See, later you cannot count, right? And you cannot adjust it, right? So better to purify as much as possible, and then when you dope it, we have got that precise control. So that's why right now we will not worry about even some good impurities are going out of this. Okay. Yeah, so this was so this was the route one. So we have removed some of the impurities. The other route of purification of trichlorosilane is, let's see, this is SiHCl3. This is a gas, and this can be decomposed into silane. So silane is another gas, but the silane is a very poisonous and toxic gas. But anyway, this we can convert this silane. So reduction process takes decomposition process takes into, and then from SiHCl3 you get this silane gas, and this silane are used for are then used to convert in the solid EGS. So this we are going to decompose it further. Now, so anyway, so we have got either SiHCl3, which is in much pure form from the fractional distillation, or we have got the silane gas, SiH4 gas. So either of them can be used. So that was step number 2. Now we move towards the next step. And again, still we have not achieved EGS. Still we are one step ahead, one step away at least. And the third step is obtaining solid polysilicon. Now here also we have got 2 routes. So you can use this purified SiHCl3, that is trichlorosilane, into solid. And this is called as Siemens process, because the reactor that what we are going to use was built up by Siemens. or you can say it is a chlorosilane process, because that is the gas what we use. And this is the complete reactor. So you can see here, obviously there is an outer shell in yellow. Then we have got, this is made up of obviously quartz, because we don't want any impurities coming from the jar itself. And then you can see there is this green line, and this green line is basically working as a seed, because see, at the inlet, we are passing this purified gas after step 2, and we are adding H2, so that this H2 will again react with whatever this, and this silicon gets deposited. So now for the deposition you require what you call it as some seed to starting point, and that is what this green what you say rod is going to do. So you can see whatever the black, that is what the polysilicon deposition which is happening. So there has to be some wastage gases. Of course, that wastage gas will be again SiCl3 or something like that, or HCl. So these gases are again purified and used. So that is how you can optimize this. Of course, you require heating, and that heating is given by the power supply. So this rod is heated at around 1100 degrees Celsius so that the deposition can take place. And you can see the reaction is, as I've said, when you are passing hydrogen gas, you get the solid. H stands for solid, because that is what being deposited on the rod, and the HCl gas is removed as a waste gas, which of course can be used later. So here silicon is deposited in the solid form, and if you see the dimension of this, it is roughly 30 centimeter in diameter, and the complete length can be about 2 meter. And this is deposited in a polycrystalline, we call it as polycrystalline. So of course this is not still pure. It is not pure, relatively pure, of course. So we want to purify it further. And there is one more point. You can see the shape of the silicon what we have obtained. It is in a shape of a rod, and this is not good for us for making the wafers. And the most important point is that when this deposition is done, this silicon goes and sits randomly. Okay, something like when you enter in a hall, especially if you enter in a class, you go and sit in the last row, right? So something like that, and then people start sitting here and there. But whatever, it is very much random, and that's why the orientation of the silicon is not in a proper manner. So instead of having a monocrystalline nature or monocrystalline crystal structure, what it forms is the polycrystalline structure. It means that in a class you sit group wise, right? You do not go and start from first bench and then go to the last bench. No, there will be some group of last bencher who will sit at the last. Then there will be some people who always want to sit in the front row. Something like that exactly happens over here. So in this class there are groups are formed, and these groups, what we call it as the polycrystalline nature of the silicon. Okay, so obviously this is not good for us. Neither in shape wise, neither with respect to the purity, and neither with respect to the arrangement of atoms. So obviously this will be broken further so that we get in a proper form. So whatever these steps I have explained till now, these are consolidated over here. You can have a look at this chart a bit later. So coming back to this Siemens reactor, this is on the right hand side. You can see that person is holding that rod, which is removed after the process of after the completion of the process. So first of all, what are the disadvantages of this Siemens reactor? Some of them already I've told you. So it produces byproducts which contains chlorine. Chlorine is a bad gas. Impurity, what is still which is present inside this rod is a problem for us. And there is another problem. We started with the rod, right? There was that what we call it as seed rod. So if there are certain impurities which are present in that seed rod, obviously they are still there. So these impurities we cannot remove. So you can think this whole process as multiple what you say purification, or what is a multiple filtering. So every time we are going to remove either the quantity or the quality, I mean the type of the impurity. The other problem is deposition process is relatively very slow, so the production rate would be lower. You can see I've named some of the companies over here. You might not have heard about this. Apart from Mitsubishi, I suppose MEMC is one of the very leading company as far as this production is concerned. We can have another route, and that is, you remember, we obtained two gases. The earlier process, Siemens reactor, works on the trichlorosilane. There was another gas which was silane, SiH4. So we can use this silane for solidification of silicon. And this process is called as FBR, or fluidized bed reactor. So here I will show you the diagram and you will understand it better. So you can see here the silane enters from the top, and then there is a what is called as kiln or something, and then this silicon seed particles are already there. But you can see that silicon seed particles are absolutely small. Okay, and they are these gases keeps so gas flow is adjusted such that these what to say seed particles remain in the air. Now, when the gas passes at very high temperature, about 600 degrees Celsius or so, the decomposition of this silane starts taking place. And then the concept of seed remains same here. So on this seed, slowly the silicon will start depositing. Whatever the rest of the gas, that is hydrogen product gas, it is going to go out as a waste gas. And what happens now, the size of these seed particles goes on increasing, and you can see that it is suspended in air. So as this weight, till this weight is very small, it can remain suspended in the environment as a particle. But when the deposition grows, the weight increases, and obviously now it cannot sustain, and it starts falling down. And when that a certain particle size is achieved, it will fall down from this particular mesh, and this is what the silicon we are getting in a solid form. Now the advantage, of course, we are going to discuss the advantage in later side. So you can see the weight increases, it falls, and you can collect it, and you can take away those silicon which are now in much purer form. So what are the advantages, especially compared to the Siemens reactor that what we studied? So you can see in Siemens, it was a batch process. You put the seed rod, the deposition is complete, you remove the completed rod, right? But here you can see that the gas can pass continuously, and that's why always FBR is a continuous process, that you can keep on collecting whatever the particles, large particles which are fallen from that mesh, and this process can keep on continuing. Okay, so it's not a batch process. So other thing is the silicon is not at all coming into contact with any of the surface. So that's why whatever the purity, it is much higher compared to what we have seen in Siemens reactor. And here HCl is, or any other gas, is not the impurity. SiH4 is passed. It is broken down. Silicon is deposited. So what is remaining is just the hydrogen, and this hydrogen is obviously not a toxic gas. So this is better. Higher production rates, the low decomposition temperature of silane compared to the previous one. So obviously the energy requirement is much lower, and that's why it is more efficient with respect to energy usage, and it requires about 1/10 of the energy as compared to Siemens reactor. And also it doesn't require state-of-art technologies, so the capital cost is also lesser as compared to the traditional processes, which is the Siemens reactor. So obviously people are moving towards this FBR, which is a better process. But whatever process you use, either Siemens or what you call this FBR process, still there are certain problems. Okay, so what are these problems? Still the atomic arrangement of the silicon is not in a good form which we want. Still it has got multiple crystalline and a variety of crystalline defects. And certainly if you see the shape of the material which is formed, it is not good for device fabrication. To give idea, the processors, your what you say, Intel or any other processors, what you make, these processors are normally made nowadays on 10-inch or 12-inch wafer. Okay, just to give a perspective, the potato wafer what you eat, it may be what 1 inch, 1.5 inch diameter. Now we are talking about 12-inch diameter. But if you have to appreciate, understand that the thickness of this wafer could be around 500 micrometer. Okay, and that has to be what you say, absolutely uniform in thickness, uniform in any other quality. So that is what the what the challenges are. So still we have got lots of challenges. So but certainly this whatever we have produced is not good for device fabrication. We have to make wafers so that we can and let me tell you, on 10-inch wafer you can have what is it, thousands of processors. Okay, however, as far as solar cells are concerned, whatever the size, it will be only one cell. Okay, and then EGS is not obtained in the proper size, as I've said, circular or square, whatever, it is not obtained. So whatever we have electronic grade we have obtained after this third step, then we will enter into the step 4, so that now we will look at the good atomic arrangement as well as the shape simultaneously. So the first process we will do is the ingot making. So we'll transform this what you say, AVR output or the Siemens reactor output, so that we get a cylinder which is say of 8, 10-inch, 12-inch or whatever the size we require. And that cylinder, when we will size, we will get a circular shaped wafers. Okay, so this ingot making process, two processes are followed, CZ and FZ. Or Czochralski process is what the widely used process. 90% of the wafers today are made by this CZ process. And then there is a float zone process, because to overcome certain problems of CZ process, the second process is developed. We will see into these two. So now starting with the CZ process, a very widely used process, you can see that there is a crucible again made up of quartz. Okay, then you have got this is the silicon ingot, but you start with one seed. Again you start with this seed. Okay, and there is a seed holder, and there is an arrangement so that we can keep on rotating it. Rotation and pulling. Rotation because to achieve uniformity, pulling because you can see in the crucible we are melting whatever the silicon which is obtained in the previous process after step 3. So this liquid is getting converted into the solid. So for liquefaction we require heater. So now what happens is, this seed what we are going to use is what you say, deposited with some deposition process, and where the CD has got very precise atomic arrangement. Let us say 100 or 111, whatever we desire. Okay, so this seed is very small, but the atomic arrangement are perfectly what we have. Now in this melted silicon we can add the dopant, whatever we wish, either B or P, and depending upon that we can have P type or N type of silicon. So you can see that we have removed the impurities, and now when we add this B and P, we can add it in a controlled manner. So we know how much this B or P, whatever that dopant we have in this melt, to a very precise level. So the orientation of this ingot will be will be dependent on whatever is the seed that we have started with. So this seed will be initially lowered. It will touch this melted silicon, and what happens is now this seed is controlling how this silicon is going to get attached with the seed. Molten silicon going to get attached with the seed and how it will sit. Okay, so when it comes into contact, suppose that this is the seed, what is a level we have, the new silicon atoms will absolutely sit as per the arrangement we already have. So that's why whatever the arrangement, let us say suppose 100 is in the seed, then same arrangement will be followed throughout this ingot. So slowly you are going to touch it and you are going to move it up. So by the cooling, the molten liquid silicon will get converted into solid. You are going to pull it up, and you are going to rotate it so that continuously silicon atom are being, they get settled here, and you move towards lengthening this input. So I can show you this process with this GIF. Okay, you have got a crucible. It is loaded with the polysilicon which we have obtained in the previous one. Okay, even some of the recycling can also be done. It is absolutely melted, so you have got polysilicon melted. You use magnetic fields so that you do not add any impurity. Now this is the seed which is lowered, and then you start pulling, and you can see the top or neck of this is formed, and this is counter rotated so that you mix as well, and you have the uniformity. You keep on doing this process, and then ultimately what you get is the final ingot. And this obviously it is cooled in a phased manner, so the cooling arrangements are also done. And then whatever is the rest one, obviously silicon is costly, right? So we keep on recycling this. We'll talk about the recycling at the end of this particular topic. So you can go through this CZ process. It's very straightforward. Okay. So now we can say that whatever the ingot we have is of the level 99.99s, and that what we can call it as now electronic grade silicon. Okay, so this is what the actual picture is. So let me give you some statistics about this. The speed of this rotation and the pull-out rate determines the defect level. If we do it too fast, there will be a lot of defects. However, if we pull it too slow, the production rate will be very slow. So that's why obviously this is how everything determines the cost of the wafer itself. Okay, so you have to optimize at every point. If this cost goes high, definitely the solar cell cost is going to go high. But if you are having too many defects, even if you decrease the cost of the wafer, you will end up with having a poor device with a poor efficiency. So ultimately the cost is obviously going to go up. So every process at every step is ultimately going to define the grid parity. Okay, so that's why it's a long chain, and that's why it is a absolutely interdisciplinary process that what we have to understand. This melts at around 1400 degrees Celsius. The ingot diameter, it depends. This is now I'm talking about 300 mm. So the wafer size normally we talk about in terms of inches. So it can start from 2 inches up to 12 inches. So depending upon the requirement, you can make the ingots, and the length can be about 1 to 2 meter from end to end. And the pull rate typically is 2 to 5 mm per minute. So let us say you want ingot of 2 meter. What will be the total processing time? Can somebody calculate it quickly? Let us say 5 millimeter per minute is the pulling rate. Okay, and then you want to have 2 meter long ingot. So what is the total time taken? Shivam Tripathi. Shivam Tripathi. Shivam Tripathi. Sir, what excuse do you have today? Any excuse? Okay, fantastic. Pradipta Rahul. Pradipta.
Yes, sir. Yes, sir.
हाँ हो क्या अच्छा ठीक है हाँ तो मैंने what question I asked
Means pool rate at 2 to 5 millimeter per minute. So
you
we
are
have to
reading
find
what
the.
हाँ you have to find out so
So
tell me the answer you know the question right huh
doing, so it will be 2 point something, 2.8.
yeah what is the answer anybody
6 hours
3
40
hours.
minutes.
6 hours okay so roughly
400 minutes.
so roughly in hours right so 6 hours and so obviously you can understand how critical the whole process would be and the typical weight of this would be between 50 to 100 kg. Again, it depends on the size and length and whatnot, but you get the idea, right? So somewhere around 100 kg, 2 meter long, and that is what, and about 2 to 12-inch diameter, and that is what you are pulling it out. Okay, so of course you can understand that the top section, this is in triangle. Similarly, at the bottom, these are not used, so you have to cut it. That is the wastage. So these tops and tails, what we call it as, it is wasted. But understand that it is not in that this size. It is not this size, but still it is an electronic grade, right? So you can use it for PV industry, so that you see in PV we have to reduce the cost. In electronic processor industry, cost is not really issue, right? So such a wastage is always given to the PV industry, and PV industry is happy to receive it because they get electronic grade at a cheaper price, right? So this is the most commonly used process, and as I said, 90% of these ingots are like that. So you can see here about 2 meter of this, and this is what the ingot looks like when it is out of the industry. Can you tell me why this person is with that coat? Is it due to corona?
Impurities.
Temperature.
Yes, so the point is that you want to avoid any impurity which is going on over here, right? So that's why you can see the hand gloves, you can see the coats, you can see the heads are covered. So absolutely no release of any of the anything from your skin or from your body. Okay, so that's why this industry requires. Okay, at that time I can tell you this is called as whatever they are standing in. This room is called as clean room facility. Clean room means it is absolutely clean, and it is given by class 1, class 10, and class 100. So class 100 is roughly what you can say 1 ppm is the impurity level, but when you go to class 1, it has got 1 ppb impurity level. I mean the purification of purity level of the air, that is what we are talking about. Okay, so they will have incredibly high purity. So class 1 rooms will be absolutely costly rooms to maintain, because you have to purify the air continuously and you have to take n number of measures. And other thing is, he is holding one gun. Okay, now this gun is called as now this is particularly, she is checking the what you say uh, uh, what you call the morphology of this. But sometimes you can also spray the nitrogen on this, so that oxygen doesn't go and sit on the this what you call it as the wafer surface. Okay, here some cracks are determined. These are all non-contact measurements one can do to find out if there is any problem in the what you say ingot which is being produced. Okay, so what is CZD is widely used, but there are certain problems. There are certain disadvantages of this particular process. Now, whenever the uh, at high temperature the silicon is made, and it is only suitable suitable crucible for the applications. And this quartz crucible, whenever we are using, there are certain impurities which can come into come into the contact, and special this impurity would be oxygen. So oxygen is anyway is very bad for us. And what happens is, as we are adding some what you say dopant, especially boron, this boron reacts with the oxygen and it forms B2O5, and such a compounds can act as a recombination center. We'll talk about that in our next fundamentals of semiconductor. So due to this recombination, it reduces the minority carrier lifetime. So if we want a good device, it doesn't matter whether it is a processor or solar cell, we want recombinations to be low, such that the minority carrier lifetime are quite high. Okay, so to avoid such a compounds which are going to act as a recombination centers, you can couple, instead of just the heating, you can couple it with magnetically coupled process, so the contact is minimized. And instead of using boron, it can be replaced by gallium as a dopant, so that this gallium is now not reacting with oxygen, so there is no question of this B2O5 or something like that. Okay, so quartz impurities, they also come into contact, and sometimes it can pass. So these are the problems what is happening with the CZ process. So that's why we go for another process called as float zone process. So you can see here again, you start with some state, there is a rotation. Okay, these are common things. Now the only point is that instead of hitting the whole what is a polycrystalline in a crucible to avoid all those impurities, you what you call it as, you move this in zone of this melting the silicon. So you have got this polycrystalline EGS, which is obtained after the state 3, and then you locally melt the silicon, and during this the impurities are driven away, and then you cool it with rotation and other cooling arrangements, and then what you get is here is the seed. So seed crystal, everything will be now absolutely in arranged pattern, whereas here it is not in arranged pattern. So polycrystalline rod is converted, whatever. So this rod, obviously you are going to obtain by the Siemens reactor only. So now this is the combination which is coming up. So if you want to use float zone process, which is used for very highly pure compared to the CZ process, but then the Siemens reactor has to be used. Okay, if you want to use the other process, CZ process, then definitely you are going to use FBR. Now one of them is a bad process relatively, right, compared to its mate, right? So you can use this, you can do this melting by induction heating. And now earlier we used to put the dopant in the molten silicon, but here that's not possible. So instead of putting the in powder form or something, you put here in terms of the gases. So these gases are passed over in this melted zone. But the point is, in FZ process you get higher quality silicon ingots compared to the CZ process, and as this process would be slower, this is a very expensive process compared to CZ. So this is what the arrangement you can see in the 3D. One side you have got polycrystalline, one side you have got the crystalline or EGS material, and this is the RF coil which will be heating here, and you can pass the gas, and it starts cooling down. You get the whole process. Okay, so this is how in the 4 steps we can obtain the silicon in the most purest form, which can be used for the or we call it as electronic grade silicon. Okay, but of course this is mostly used for the processor industries or electronic industries, we call it as, but it's very costly. 4 steps have gone for the purification, and we don't want that much of performance over here, right, in solar PV. So that's why we are going to compromise with the cost, and for that we can go for polycrystalline silicon ingots. Okay, So that part we will discuss in the next lecture, so that we will stop here and we'll finish the what you call the rest of the chapter in on coming Monday's lecture. Okay. So any quick questions?
Sir, hello.
Yeah. Go on, please.
Sir, in the quiz, there was a question hour angle on equator. So, sir, hour angle will vary for a particular place throughout the day.
So what's the location I'm talking about?
It's equator.
Yeah. So please check the slides. Okay. So the answer would be there. Then we will see. Answer is already there in the slides. Okay. Any other question? No. Okay then. Thank you all. So let us finish this meeting. Thank you. Bye. Have a good weekend.